Stimați membri ai Academiei de Științe a Moldovei, distinși cercetători științifici, onorați oaspeți, bună ziua! Astăzi, 30 iunie 2026, o zi așa fierbinte, dar fierbinte nu numai în sensul temperaturilor înalte, dar și în sensul unui eveniment așa foarte important pe care noi împreună îl organizăm, Masa rotundă, Știința și tehnologiile cuantice, dedicată lansării Inițiativei Cuantice Globale 2026-2030. Vreau să menționez la bun început că Academia de Științe a Moldovei a fost activă în toate inițiativele care au fost parcursul ultimilor ani și vă reamintesc că chiar încă în 2021 a fost o hotărâre a prezidiului pentru a crea o platformă de comunicare științifică, științele fundamentale pentru dezvoltarea durabilă a societății. Și în fruntea acestei platforme a fost domnul, de la bun început, domnul profesor Vladimir Fomin, colegul nostru și membru de onoare al Academiei noastre, care a fost foarte activ în parcursul acestor ani și în contextul participării dumnealui la o conferință la Universitatea Tehnică care va avea loc mâine și împreună am luat decizie de a organiza această masă rotundă. Dar interesant este că totul a pornit de la o decizie a Organizației Națiunilor Unite și deci anul 2023 a fost declarat anul științelor fundamentale pentru dezvoltare durabilă. Deci vă atrag atenția la faptul că noi am participat la mai multe evenimente organizate la scară internațională și ceea ce a urmat deja, deci Organizația Națiunilor Unite la 25 august 2023, mi se pare, sau 24, deci a declarat deceniul internațional al științelor pentru dezvoltare durabilă. Și deceniul este din 2024 până în 2033. Și în contextul acestui deceniu, bine, iată, a fost la Chișinău și președintele Consiliului Științific Internațional, domnul profesor Peter Gluckman, care a avut și o prezentare în sala Azurie în aprilie. Și deci la nivel global a urmat anul internațional al tehnologiilor cuantice, anul 2025, după ce a venit inițiativa UNESCO, Inițiativa Cuantică Globală, acoperă anii 2026-2030. Și eu aș menționa, da, comunitatea noastră este foarte activă, noi avem cercetători care activează în aceste domenii, dar eu aș totuși scoate în evidență două personalități și asta, deci în Statele Unite este academicianul nostru Isaac Bersucher, în care deci având o vârstă destul de înaintată, dar este activ, cel puțin mai apare câte o monografie și vă atrag atenția la faptul că academicianul Isaac Bersucher a creat laboratorul de chimie cuantică încă în anul 1959. Și desigur că noi urmărim și chiar ne bucurăm de faptul că rămâne vizibil la scară internațională și de fapt ne duce faima nu numai a Academiei Științei a Moldovei, dar a țării noastre în lume. Și în Europa, în Uniunea Europeană, este foarte activ, după cum am menționat deja, domnul profesor Vladimir Fomin. În context vreau să menționez că chiar recent a fost ales membru sau, cum se spune, fellow al Societății Europene de Fizică. Și asta este, de fapt, aș spune, un succes foarte, foarte vizibil, foarte mare și să-l felicităm pe domnul profesor Vladimir Fomin pentru că succesele dumnealui sunt și succesele Academiei de Științe a Moldovei. Dumnealui fiind membru de onoare al Academiei noastre, dar pur și simplu participant activ la multe evenimente și chiar inițiator. Iată cum masa aceasta rotundă a fost inițiată de domnul profesor Vladimir Fomin și eu aduc mulțumiri tuturor care au pus umărul să organizăm această masă rotundă. Lumea se schimbă foarte rapid. Știința se dezvoltă cu pași gigantici. Deci, desigur, iată, noi am avut oaspeți foarte înalți, profesorul Randy Shankman din Statele Unite ale Americii, care a venit la aniversarea de 65 de ani a Academiei noastre și care a menționat, printre altele, că și același lucru a făcut-o și Peter Gluckman, că spre regret, dar în unele regiuni ale lumii, atenția acordată științei nu este cea așteptată. Și asta, în primul rând, ține de finanțare. Și aici, desigur că aceste evenimente care noi le organizăm, ele trebuie să amintească și societății și guvernanțelor că o știință care ar face față exigențelor trebuie susținută financiar la nivelul cuvenit. Și cu atât mai mult este era inteligenței artificiale, era tehnologiilor cuantice, când deja și suportul trebuie să fie respectiv. Eu, iată, am vizitat câteva țări în ultimul an, vreau să vă spun că doar în China am văzut acel suport, care probabil că satisface exigențelor timpurilor noastre. Deci, și doar în China am văzut că ei nu au probleme cu tineretul. Dacă în toată Europa spun că în domeniile tehnologiilor, în domeniile fizicii, matematice și așa mai departe, deci nu știți că este science, technology, engineering, mathematics, domeniile acestea, păi în China nu au probleme. Ei nu au probleme. Acolo, eu poate o să vin cu o informație cu ocazie, dar vreau să vă felicit încă o dată în numele prezidiului Academiei Științe a Moldovei pentru faptul că am reușit împreună să organizăm această masă rotundă, să-i aducem mulțumiri domnului profesor Vladimir Fomin pentru inițiativă și chiar insistență, că dumnealui așa este un motor, dar și celor care au realizat. Aici este secție, este domnul profesor, domnul academician Vecislav Ursache, este pe... Este, da, Vecislav Ursache și tuturor, pentru că orice eveniment, el poate fi realizat cu succes dacă sunt participanți. Iar astăzi avem participanți și aduc tuturor mulțumiri. Iată aici, printre cei care astăzi vor avea prezentări, și domnul profesor Macoveș, domnul Cancean Sidorencu și domnul membru corespondent Vladimir Țurcan și sistemul hibride cu atom artificial, domnul Ceban și domnul Cancean Ursache va face concluzii. Da, dacă sunteți de acord, atunci cu permisiunea dumneavoastră, declar masa rotundă cu genericul Știința și tehnologiile cuantice, dedicată lansării Inițiativei Cuantice Globale 2026-2030, deschisă. Succes!
Domnule președinte, doamnelor și domnilor, eu vă mulțumesc din toată inima pentru felicitările cu ocazia alegerii mele ca Fellow of the European Physical Society. Mulțumesc frumos! Eu aș dori să mulțumesc domnul președinte Tighineanu și domnul academician Ursache pentru organizare, pentru coorganizarea mesei rotunde de azi. Mulțumesc. This UNESCO Global Quantum Initiative, as represented in this introductory slide, was launched in order to make the development and application of quantum technologies worldwide more uniform, more inclusive, and for the common good of the all peoples on the earth. Maybe one point to be proper, to be clearly understood. Until now, the investments to quantum technologies are more than 55 millions of American dollars. Billions, it's huge investment. But the majority of countries do not use the potentialities, the fruit of these developments. And according to UNESCO, there are 150 countries, more than 150 countries on the earth who even do not have now a national quantum strategy. I like to ask you, and especially the president, is there a national quantum initiative or strategy in the Republic of Moldova at present? No. This is a confirmation of the position of the UNESCO. UNESCO wants to make this development more uniform and more accessible to all countries, to all people. And I think one of the main goals of our round table will be to contribute to elaboration of such a national strategy. Certainly our role is consulting, but the results of our conclusion must be brought to the decision makers in the Republic. UNESCO determined 5 strategic objectives. No time to go in depth, but first of all, it's advancing quantum education and strengthening capacities for that. Here are representatives of the academy of 2 universities, and this must be clearly put in the context of the development of education. It must be education towards the goals of this quantum initiative. I had the pleasure to talk yesterday to the new rector of the State University about this problem, and I ask colleagues who will be today at the Senate of the Technical University to do the same. Second, building sustainable quantum infrastructure and enabling resource sharing. Certainly, this infrastructure will not be built everywhere, not in every country. I cannot foresee that it will be specially built in the Republic of Moldova. But due to collaboration, to strong scientific and other interactions, the colleagues from the Republic of Moldova can, and they are already obtaining a link to the modern infrastructure. I think academician Sidorenko will speak about our recent effort in this direction. But the project Rebrain, which was launched in the Republic of Moldova to attract the representatives of the academic diaspora from Moldova, is working, and this is one of possible ways. Third, advancing public awareness and societal engagement. I think this round table and its conclusions must be brought to the attention of the broad public, not only to the government. 4, strengthen international cooperation. I already mentioned that. And 5th, foster responsible quantum innovation and anticipatory governance. This is another very important point, which is not so easy to realize, but is necessary. One should monitor the needs. One cannot simply develop quantum technologies from some abstract reasons. What is needed practically for the society in the Republic of Moldova? And again, I had yesterday a very interesting discussion to one of the former collaborators of academician Tigenianu, Mihai Naki, who makes this practical work to the direction of medical equipment, which is needed now, and it is based on quantum technologies, and he is capable of doing that because of the knowledge and habits of the experience which he accumulated in this academic society. This is only one short example based on my stay in Moldova during one day, but you are permanently here, and it's very important to think of practical needs and then to develop collaborations towards these practical needs. At this point, I stop with the presentation of the Global Quantum Initiative. Certainly, academician Ursaki possesses a lot of more practical information about that, and if you like, please address him. Now I make a step backwards to introduce my presentation, which will be about quantum rings, a unique platform for the quantum mechanical paradigm. 2 weeks ago, I was in Brazil as a director of an international school workshop on quantum rings. And over 1 week, together with colleagues from the whole world, including United States, many countries of Europe and Latin America, we discussed this fascinating topic. And here are only a few projections of this field of quantum rings, which are related to our discussion of Global Quantum Initiative. I will be very quick, but I must address you to the book, Physics of Quantum Rings, the 3rd edition, which I introduced here in this same small hall last October. It was just appearing from print at that time, but now it's already spread over many countries in the world. And why these are preliminary works? Why is this topic so important for quantum technologies? You are involved and you know about the worldwide work towards finding new materials, new structures, new architectures for some specific applications, on-demand applications. Demands are very different for optoelectronics, for fluidics, for medical biophysics, but one must be able to adjust the structures and materials to these demands. And one of the ways to do so is topology. You may use very simple, ordinary, conventional materials in order to get extremely interesting results because of shortage of time. In the recent conference in Rome, which was last week, I heard about enhancement of critical temperature up to room temperature, which has been confirmed experimentally already, certainly in a laboratory. Not due selection of some specific materials, which were the goal over 40 years, but due to structuring of special types of superlattices, where you have a periodic metal and superconducting, normal, conventional superconductor layers. But due to this nanostructuring, one can get enhancement of the density of states close to the interfaces. And this, in its turn, increases electron-phonon interaction and enhances the critical temperature. This is only an example apropos, but returning to rings. In fact, the topological background is founded still in 30s and 40s. Very clear picture was made by Michael Berry, which shows that if a particle, quantum mechanical particle, makes a roundabout, depending on some parameter, it acquires an additional phase. You can see here in equation number 4, the phase, dynamical phase, which you know from textbooks on quantum mechanics, but also another phase, which is called geometric phase, and which is due to this confinement to some parameter. And what can be this parameter? This parameter can be a position on a ring. If you have provided, if you have fabricated a ring, then you will have a periodic dependence of the phase on the magnetic flux penetrating the ring. It is in equation number 9. This is sufficient. You have exponential of the ratio of the magnetic flux through the ring and magnetic flux quantum. So it's a quantum effect, but you change the phase. Therefore, you can change the spectrum, the energy spectrum of a particle. And I think it is shown here. It's a schematic for one-dimensional ring, but if it is read by a magnetic flux, the energy occurs to be a periodic function of the magnetic flux, as you see. And current, which is a derivative of the energy with respect to the magnetic flux, is also periodic, as you see in the zigzag curve below. What is nice here, what is special here, that the ground state of this structure is not always the state with zero orbital momentum, like it is in topologically trivial structures. When increasing magnetic flux, you go to the state with a momentum, angular momentum, and with still high angular momentum. And it means that the current which flows in such a ring is persistent, is everlasting, is eternal, like in an atom. Though this is already a big structure, certainly it cannot be very big. It must keep the coherence over the circumference of this ring. But if it does, then we arrive at a lot of remarkable effects, like these first observations in an ensemble of copper rings, in a single gold rings, and in a lithographically prepared single gallium arsenic ring. So it was done in 90s, which I call the renaissance of this topic. but because of shortage of time, I must tell you that this field requires extremely careful handling of objects. If they are 200 nanometers diameter or 100 nanometers diameter, how to measure the persistent currents? Through magnetization. But how to measure magnetization? Okay, probably you will tell me through squid, academician Sidorenko. But the squid must be as small as 100 nanometers. It's another problem. And Dominique Maillet made something beautiful. He growed a ring and a squid on one wafer in one run of fabrication, and it costed at that time, I think, 3 months. But due to this combination of the measuring instrument and the object, he was able to detect this periodic dependence of magnetization on the flux. Further, this was a beautiful work which I always presented international conference made in the group of Professor Brandt and Moscow University, together with academician Gitsu and Professor Nikolaeva and Professor Ponomaryov, who observed the same periodic dependence on magnetic flux in bismuth whiskers, where the states are confined to the circumference. So that was really a great achievement also of the Moldovan scientist. And now I come briefly to our own work on such self-assembled quantum rings, which are in indium arsenic, gallium arsenic dots, after capping with gallium arsenic and annealing in the arsenic 2 flux. This is know-how. Look at this panel. It's an AFM image. What do we obtain? What is here, according to your opinion? What is it? It's a ray of what? Of something what has a black center. Are they dots or not? It is not possible to estimate it. And our colleagues in the Netherlands were able to make XSTM, cross-sectional STM. They cleave, they break their sample 100 times, and they make STM at the cross-section. And they obtain something which you can see here. It's a catastrophe. There is no hole, there is no opening. These are not rings, these are quantum dots which are deformed. But they should be simply connected. In simply connected systems, there is no periodic dependence of any quantity on the magnetic flux. But we took these results of experiment in order to build a model of such an object, which we call quantum volcano. It's elongated, it has 2 bumps, but it does not have 0 in the center. And for quantum volcano, with experimental data, we obtained something very interesting. In such a potential for electrons, the electronic wave function from the center, from the rim, goes down exponentially to the center. And if it goes down exponentially, it is 0. It's practically 0. And therefore, such objects are doubly connected. They are rings for electronic wave functions, though they are singly connected geometrically. Because of that, they should reveal, this is our theory, periodic dependence of magnetic moment on the magnetic field. And this was an experiment which confirmed our prediction with high precision. Experiments by measuring magnetic moment gave just an oscillation positioned at 13 Tesla, its high magnetic field, but it was in nice correspondence to our prediction. Our work costed 4 years. Experiment was also very, very carefully prepared. So one should be able that such penetration to the field of quantum structures requires patience and knowledge. This is okay. And now one can do them with laser interference, with positioning of individual atoms. These are more recent ways, certainly by lithography, by direct writing, and also by self-assembly, like it is shown here. This wonderful self-assembly. In particular, one can even build not a ring like in the left panel, but a Möbius ring. You know, you twist your crystal, which is pulled on a ball of selenium. My time goes to the end now. I have here examples of other materials like graphene quantum rings, cyclocarbons, very nice recent materials where you have on a ring maybe 18 or 16 atoms of carbon only. They are very small. They are in the scale of 200 to 100 nanometers radius, but they all give clearly dependence of their properties, like persistent current here, or optical transmission here, or magnetoresistance here, on the magnetic flux. We can influence the critical temperature of superconductors by selecting aspect ratio, height to radius of quantum rings. This is now under experimental proof. And certainly I like at the end to thank colleagues of the recent time in Germany, China, Italy, with whom we were interacting, and also my colleagues from Brazil who allowed us to organize this international school. And now I thank you for your attention with providing you an Ellis ring. What is an Ellis ring? Rings are not only in quantum solid state. They are everywhere. They are in the atmosphere. You know, tornadoes. This is also ring-like excitations of gas. But you have also quantum gases. Gases which consist of single atoms. In this case, it's rubidium gas. And if it forms Bose-Einstein condensates, in these gaseous condensates, there are elementary excitations which are called monopoles, and they can give rise to rings. They bend to a ring. And we have a ring in a gas of cold atoms. If another monopole goes through such a ring, then it turns to an antiparticle. It's science fiction, but it was observed and published in prestigious journal. In our world, in macroscopic world, it would be something like a man enters a ring and leaves it as a woman. It's impossible, but it's possible in quantum world. It's only one example of infinite potentialities which are provided by this quantum and topological effects. And I think we should go already to the next presentation of our round table. Certainly, I am prepared to answer your questions, if any.
Mulțumim, domnul Fomin, pentru această prezentare. De fapt, este a doua prezentare. Anul trecut a fost prima prezentare, de fapt, aici la Academie, dar la conferință adesea auzim acest subiect. Anul trecut a fost în legătură cu anul științelor cuantice și acum în legătură cu inițiativa care vedem că acest subiect este în plină dezvoltare, noi efecte, noi descoperiri. Dacă sunt întrebări față de profesor Fomin, cred că discutăm după masă. Da, la coffee break, la masă, după masă rotundă. Și acum deci trecem la a doua prezentare, un subiect deosebit de primul subiect cu inelele cuantice. Domnul Macovei ne va vorbi despre efecte cuantice, interacțiuni multiatomice mediate termic. Poftim, domnul Macovei.
Okay. So I would like to thank the organizer for inviting me at this meeting. And before starting, I would like to emphasize that quantum physics was always present at the Institute of Applied Physics, starting with those people I know, like academician Kovarsky, bravo academician Moskalenko, or Professor Klokishner, Professor Yanaki. And I think quantum physics will survive at the Institute because we have younger generation represented by Victor Cheban, for instance, and he is really qualified to do the science in this field. So in the next minutes, I will talk about quantum effects of light scattered by few atom systems, however, not pumped by laser field, but by incoherent field, which is a typical thermal field, like fields from different electric lamps, like this one. So, of course, the outline is motivation, why we do this. And then I will show you how to get interference effects, which everybody knows that you'll get in laser fields, and maybe less people know that you may get this even in the presence of thermal environments. And I will talk about high order correlation function between photons, and I will end up with showing how to get quantum features from photons scattered by many atoms, because we know many atoms usually behave classically, and why they will emit or scatter light, which is quantum effects. So we know from classical or textbooks from schools that double slit experiments, this is very nice, but you can get the same things if you apply a thermal field to double slits, but the idea is not to detect single photons or using detectors at the same place, but if you have two detectors at different places. So if you have two detectors at different places and the double slit experiment with the thermal light, then you get interference fringes if you change the distance between the detectors. This is a difference. So you'll not get the standard interference effect if you're using a single detector, but if you get it, if you use two detectors clicking at the same time, when you detect two photons simultaneously. But this is a difference, yes. Okay, so just starting a little bit with some simple interference effects from literature. The most famous maybe is how to get how light will propagate not directly. We know, everybody knows that if we looking at an object, then the light will propagate directly, yes. But there is a very, very, very small probability that the light will follow these free slits experiments. But the blue rays will be the probability to get this. It's quite small. It's, I don't know, 10 to minus 3, 10 to minus 4, even smaller, okay? But it's there because you have to consider all the paths the photon can get from the source to the detector. And this is a quantum stuff. And at one moment, it was a hot topic. If we talk about quantum, how, and now we have this championships of footballs, how will be and the picture was provided by Victor is here. So how the ball will go, will push it to the goalkeeper, and if both the ball and the goalkeeper will be quantum mechanically, it will be very interesting how the physics or how the life will be. But we have to mention that the quantum effects is typically the micro world, yes, and the less were almost not visible and macroscopic, yes. Our tips of interferences, if you have like a V-type free-level systems, and the photons can decay, the electron can decay either from the first state or the second state, then it can be interference from these two paths, and usually the spontaneous emission or the population on the upper states can be slowed down significantly in comparison to this exponential decay rate. So just a little bit of theory. So what we detect, so what we want to calculate theoretically, we have intensity, which is proportional to G1. This is a standard single photon detector. Then G2, this is the probability to detect two photons at the same place or at two different space positions. And also free photon detectors or free detectors in different places. And this is typically described by the third order correlation function. All this correlation business was done long time ago by Glauber, and he was a Nobel Prizer I don't know, 10 years or even more. So if we took a concrete systems, we have three atoms on the vertices of an equilateral triangle, and we have three detectors, for instance, arranged in this way. Why we took this geometry? Because it somehow makes it easy to calculate analytically, and then to try to get some insights or some results. The work was done with Artur Rotar. He's a master student, and he finished the master thesis in university, Moldova State University. So standard theory, we work with Hamiltonian, including also the interaction with the environment, and also the dipole-dipole interaction between three atoms, because these three atoms, even if it's arranged geometrically, then they can be close to each other and then can be far away from each other. And as standard, you have probably seen this many times when I presented something. We work with the master equation approach. Yeah. And usually we have two types of interaction between atoms. This could be coherent dipole-dipole interaction. This is this flip-flop. Mm-hmm. When you get one photon from another and you give it back, this is dipole-dipole interaction. But can be also incoherent interaction when these two atoms can decay faster because they interact collectively via environment. Mm-hmm. So we have both. And then because it's just three atoms, we form all these decay states, possible combination of these three atoms, one being in excited state, another in ground states, or all three in ground states. And then the energy diagram will be like this. And this omega big is dipole-dipole interaction between the atoms. So this is like three atoms will be equivalent to the single 8 level atoms. And this makes a little bit more easier to analytically do the calculations. So the first step, we calculate the populations of these levels, collective levels, yes, in two different situations. When the atoms are very, very close to each other, this is represented by this chi equal with 1, and more realistic when the atoms are not necessarily being close to each other. I mean close, I mean on the scaling of the emission wavelengths. It's larger than the emission length when you may get independent atoms, and starting approaching each other on the emission wavelength scale, or even smaller, when the atoms strongly interact collectively, including dipole-dipole interaction. So why in one case we have all state populated, in another case we have only this 4 state populated? Because usually it's known that in many atom systems you have the superradiant states and subradiant states. Mm-hmm. Subradiant states are some states, collective states, which are really hard to populate them. Even if you populate them, then they will decay very, very slowly. And why this is important now? Because if once you put the population there, then you keep this energy for a longer time. But somehow you need to extract it from there. So still works are going on. So in one case, these antisymmetrical states are simply decoupled and they do not play any roles if the atoms are close to each other. So this is the difference. And of course, we, as a first example, we calculate this second order correlation functions for these systems having just two detectors at different positions. And what we observed, we can get values for this G2 around 1, smaller than 1, and larger than 1. If you are around 1, this means you have coherent light. But don't forget, we pump with incoherent light. Yes, and then you get like lasing at that output. If this G2 is smaller than 1, then you get quantum features. And of course, if this is much larger than unity, you get super bunched photons, like this one. So as a result, we got, for this G2, we got all this kind of photon statistics, just pumping with incoherent field. But there is a difference that you have also changed the position of detectors, because you will not get this quantum features in any point of the space. It's just in certain directions because it's interference, as you know. As a second results, we calculated third order correlation function. This means 3 detectors in different position, and again you get interference. But why we did this? Because we wanted to compare G2 and G3 just to prove that we have single photon detection or we have 2 photon detections. And what we get at the end, that G2 is smaller than 1. And this means you'll get at the output 1 photon. And G2 is smaller than G3. That means just to get 3 photons at once, it's almost, the probability is very small. So this means in certain directions, you'll have photon emitted 1 by 1. And this is quantum effects, because classically photons will come in a bunch. Like in banks, sometimes you go on the shopping and it's a lot of people, and sometimes they go, nobody's there. This is classical. Quantum will be 1 by 1. So this is the difference. So this was our recent results. We expect the final decision of referees will be in, I don't know, in a few weeks. And I will turn to the second part. What will happen if we have more atoms? Because the previous, in the first part, we talk about 3 atoms, and you may say that, okay, if you have 3 atoms, this is usually a small system, you may expect quantum features. What you will get if you have more atoms in the system. So the procedure is the same. We work with the Hamiltonian, we work on the master equation approach, but we keep a difference that the atoms are really close to each other on the emission wavelength scaling, and the dipole-dipole interaction are really strong, static dipole-dipole interaction. And why this will make a difference once the dipole-dipole interaction is very big, yes. And these states we have observed between symmetrical and antisymmetrical are the difference, the energy difference is a dipole-dipole interaction. Then you get a big splitting between this collective symmetrical and antisymmetrical states. Once you get this different splitting, it looks like you are out of resonance, okay? For four, it's not quite resonance because you are thermal field, which is broad, yes? But still, you will get the dipole-dipole interaction entering in the system, and this will make the difference. So this is the idea. So we calculate this G2 for different number of atoms, and what is interesting here, we compare the results when you have the dipole-dipole interaction, this is the blue line, and when you have the without dipole-dipole interaction, this is the blue line, and with dipole-dipole interaction, including but strong dipole-dipole, this is the dashed line and the green line. So what we observe, that even for bigger number of atoms, you get the quantum feature, this G2 goes below unity, just because you have this strong dipole interaction between the atoms, and you have many atoms. But even if you have many atoms, yes, you have strong dipole interaction, but X a little bit larger, this means because it's proportional with the temperature, this means that you have weak temperature. This means you have a weak thermal field. You have a weak thermal field. From that ensemble of many atoms, you will just excite a few numbers of atoms, and this few number of atoms will give you quantum feature. Or for you have a big ensemble of atoms. So this is the idea. You have many atoms, you have a weak thermal field, you excite few atoms, which give you at the end these quantum features. So again, we wanted to show that the G3 is smaller than G2, and it's really the case. And again, we have inset which compare the results with dipole-dipole interaction and without dipole-dipole interaction. And it's really, we showed that at the end, G2 is larger than G3, but below unity, which is a quantum effects, and in a many atom system. We're trying to understand this and hope to submit the work in this year. And I would like to just end with the conclusion that dipole-dipole interaction entering in the business change the photon statistics, but they really should have to be strong. And of course, this is a theoretical treatment, keeping all atoms fixed. They are just two-level atoms. They are close to each other. That as a theoretician, I can imagine this. In experiments, things will be a little bit harder and even harder, but still works on these collective atoms experimentally are performed, and they are published well and rapidly in high-ranking journals. And thank you for your attention.
Da, mulțumim, domnul Macovei. Dacă sunt întrebări, da, poftim.
First of all, I like to highly appreciate this very motivating work, which in my view is a beautiful example of the scientific heritage of academician Victor Kowarski extended over decades. Second, again, your results show that this multi-photon processes in quantum systems are another vivid and clear example of application of quantum mechanical paradigm, which you demonstrated very clearly. And therefore, I have only one question, but I'm afraid it's a complicated question. To the best of my knowledge, in Germany, there is Max Planck Institute for Photonics in Bavaria, in Munich. Also other institutions in other cities. Have you attempted, or maybe you have already established some kind of collaboration with them or with some other European institutes who have direct access to eventual users of this multi-photon processes in real applications for future industry? What is your vision in this direction? Thank you.
Okay, I got the point. So if with respect to the application or working with the experimentalists, so unfortunately I do not work with the experimentalists, but we do work with the people from outsiders, including Germany or Romania. This is true, but usually we do just theory. Maybe we are few or two, not so many people, so just spread also on the experiment. Maybe, but I understand. So this is a like weak point. So I do not work with experiments.
It's a wish for the future.
But maybe yes, maybe.
Da, mulțumim. Dacă mai sunt întrebări, dacă nu, în particular, înseamnă că discutăm. Vedem cât de diverse sunt preocupările cercetătorilor noștri două prezentări absolut diferite ambele din domeniul fizicii cuantice și diversitatea va deveni și mai posibil și mai larg vizibilă după prezentarea următoare a domnului Sidorenko, deoarece este vorba despre rețele neuronale inspirate de creier. De fapt, la baza fiecărei revoluții industriale, inclusiv la industria 5.0, care acum practic se începe, a stat oarecare descoperiri fundamentale și a fost o tehnologie de bază pentru ele. Deci prima revoluție industrială a fost bazată pe mașina cu abur, a doua industrie industrială a fost bazată pe electricitate și motorul cu ardere internă, a treilea a fost bazată deja pe apariția energiei cuantice. Peste tot a fost legată și cu energie. Energia cuantică și descoperirile tranzistorilor, etc. A patra revoluție a fost legată de microelectronică. Deci atunci când Intel a început microprocesoarele 40, 80 și așa mai departe, deci și s-a început această dezvoltare industrială. Acum ne aflăm la o etapă când nu există o tehnologie fundamentală care reprezenta bază pentru industria 5.0. Sunt diferite descoperiri, nanoelectronică, în biologie, în medicină, un număr foarte larg de descoperiri, dar nu este o tehnologie fundamentală. Posibil că anume această legată de fizica cuantică, deci calculatorul cuantic și inteligența artificială sunt două elemente care, sinergia dintre care ar putea reprezenta o bază pentru această industrie 5.0. Și acum îi dăm cuvântul domnului Sidorenko să ne povestească despre această componentă și posibil legătura dintre calculatorul cuantic și inteligența artificială, deoarece sunt lucruri absolut diferite, dar sinergismul ar da un efect esențial, cred. Da, poftim.
Thank you very much. You're absolutely right that nowadays the quantum mechanics penetrated in all areas of human activities. That's why no wonder that the microelectronics, which intrinsic based on quantum mechanics, also is one of the example of this penetration. But first of all, I would like to mention in general that quantum mechanics, we celebrate 100 years of discovery and triumph of quantum mechanics. And Moldova has own experience and great personalities who worked, who are belongs all over the world, know the names of Isaac Bersuker. Quantum chemistry, it is the same quantum mechanics. That's why what is chemistry is the physics of the upper shells of atoms. That's why the personality like Всеволод Москаленко, Stanislav Moskalenko, Viktor Kovarsky, Isaac Bersuker, this is the older generation who founded here basis for further development. And nowadays, today talks, it was children and grandchildren of these scientific grandchildren for these great personalities. Thank them, and the progress goes on. And today we have seen already some examples of this penetration in reports of Professor Fomin and Professor Makovey, and I would like to give some such examples of implementation of ideas. First of all, ideas important, because if you have a prospective idea, it can be implemented. The results of implementation of quantum effects for construction of artificial neurons and synapses and further development of the artificial neural network. It was the goal of the SpinTech project, European funded. Nowadays we have with our partner from Netherlands, University of Twente Erasmus project. In the frame of this project, our master students goes there to make master work and then doctoral thesis. That's why this activity goes on. But first of all, I would like to outline what I am going to speak about. First of all, the motivation of the work, why nowadays it is so popular and so worldwide investigated, artificial neural networks. Then I will give some examples which we deal with. Then existing not superconducting at room temperatures existing artificial neural network. But then I will explain why it is necessary superconducting solution. Key word energy here. Then some novel ideas which need novel technologies which were developed. And then I will give some examples of our successful implementation of artificial quantum devices like Josephson junction for realization of artificial neurons, but at the same time, they are base element for quantum computers. That's why this is one universal instrument, Josephson junction, which can be base element for neuron, and at the same time, this is base element for quantum computer. All of you knows this famous Moore law. This is the empirical law that very rapid, exponential, rapid development of microelectronics, number of transistors in computer, number of cores and so on. But last decade, it goes to plateau. All generations of computers, including this one notebook, which I use for presentation, based on idea. I told that the main is idea. Idea from John Neumann. He proposed the von Neumann architecture. This memory block and the program block, and he created the first computer for Neumann machine based on the vacuum tubes. On the right corner, you can see this. Now, just in museum, one can meet them, but the first ENIAC machine, electronic numerical integrated on computer, he created it in 1946 to resolve the nuclear Manhattan Project, and this architecture was so useful that further four generations after development of transistor, instead of vacuum tubes, was IBM company, or at that time it was Philadelphia Battery Company. Then later it is IBM. They used, instead of vacuum tubes, transistors. Then the third generation, as we entered in technical university, it was exactly the third generation of computers based on chips. In single chip, many thousand transistors. And also IBM famous 370 system, which based on semiconductor integrated chip, including many thousand transistors. And the fourth generation, including this notebook, which use also von Neumann architecture based on cores. Core consists of many chips, but nevertheless, the architecture is the same: memory block and program block. And all was perfect, but the treatment, archivation, and transmission of information needs huge energy amount. That's why here you can see this one of 700 data center of Facebook all over the world. A lot of such data center, and it works in Sweden. 9% energy of very well developed industrial country, Sweden, they use. Single transistor use a very small amount of energy, but trillions of transistors total use a lot of energy, 120 megawatts, only one data center. Progress, it is not possible to stop. That's why it will be more information. It will be online transmission of videos and so on. That's why we cannot reduce the information, but we can reduce energy consumption. That's why what will be the 5th generation of computers? Hint gives our brain, because our brain is much more complex than all computers existing, but instead of 120 megawatts, it uses only 20 watts. 20 watts, it is huge energy for brain. Usually people use 10 times smaller energy, but 20 watts, when Professor Fomin is working on his work, preparation of project, or teaching students, or women in store. You see, women in store shall compare size, color, model, a lot of things in store. That's why brain shall do a lot of, to treat a lot of information, and this period of time brain can power consumption up to 20 watts. But this is maximum, and it is incomparable 5 orders of magnitude less than the existing data center. That's why it is just hint to try to change the architecture from von Neumann architecture to brain-like artificial neural network, where neurons are connected by synapses. Synapses give different weight in the brain, and many layers which treat information. Base elements of artificial neural network are neuron. Neuron is analog of transistor. It is a switching element. And synapse, this is a linear element which shall change from 0 to 1 the strength of connection between neurons. That's why the famous IBM company, which prepared 4 generation of von Neumann computers, they prepared successfully and brought to the market the IBM True North brain-like artificial neural network computer using the same switching elements, transistors. On the right corner, you can see artificial neuron consisting from approximately 30 transistors, and artificial synapse. Transistor is intrinsic nonlinear element. That's why linearization of characteristics of transistor is difficult technical task, but engineers successfully resolved this task and prepared linear element artificial synapse from something like 30-40 metal oxide semiconductor transistor MOS. And here one can see that this is a plate with processors, IBM True North, and some other generations of such INN. They successfully were used for different access. For example, nowadays the bus or a track without driver, no wonder, and who is operating IBM True North neuromorphic computer is artificial driver. Or recognition of terrorists in crowd, it is also very rapid to treat a lot of information and to compare different features. It is the task for INN. But you can compare this computer BERT 2017 was created, 1 kilowatt, and brain still much less, 4 orders of magnitude less. That's why the architecture we can use like brain, but elements should be much less energy consumption. For this purpose is very promising the superconducting switching element, Josephson junction, which can be, as I previously told, the base element for neural network, but at the same time for pure quantum computer. But the working process is pure quantum mechanical. That's why it is the same base element, but for different purposes. For implementation of superconductivity does exist several opportunities. One of them was proposed many years ago by Anatoly Ivanovich Larkin and Yuri Nikolaevich Ovchennikov. They proposed to create superconducting ferromagnet. It is very strange. It is like hot ice, something like this, because they are antagonists. But they, in theoretical work, they proposed if does exist such superconductor ferromagnet, in that case, the Cooper pairs between two subbands, because in ferromagnet, conducting band is split into two subbands dependent on direction of spins, so, spin up and spin down. That's why two subbands. And if we can imagine creation of Cooper pairs, here are presented, such Cooper pairs will have non-zero pairing moment. Non-zero pairing moment will lead to the pairing function or order parameter oscillating in space. Very strange superconductor. In traditional BCS superconductor, pairing function or order parameter is constant in the whole superconductor, independent of the size of this. In such superconductor ferromagnet, it will oscillate and it will oscillate critical temperature of such superconductor ferromagnet. Again, we come to idea. I mentioned that the very important in techniques idea. Alexander Buzdin, he is head of theoretical department Bordeaux University. But before that, he was main partner from Nobel Prize winner Vitaly Ginzburg in FIAN, Physical Institute in Moscow. He proposed to create the sandwich from superconductor and ferromagnet. In superconductor, Cooper pairs does exist. due to quantum mechanical tunneling, the Cooper pairs penetrate in ferromagnet, they will be influenced by exchange field in ferromagnet, and immediately a pairing function will become oscillating. In such case, the ferromagnet layer will serve like Fabry-Perot resonator. Pairing function penetrate, reflect from the outer side interface, interfere, and then it will be maxima and minima. If we can tune the thickness of ferromagnet, then we can reach a maximum of minima of critical temperature. And Leonard Tagirov, our partner from Kazan University, head of theoretical department, also theoreticians. Yeah. He proposed so-called Tagirov spin valve, the superconducting layer between two ferromagnets, and then if we change magnetization of one of the ferromagnet layer, then it will serve like effectively change of thickness. That's why we can switch from superconducting from minima TC to maxima TC, to switch from superconducting to non-superconducting state. We tried to prepare, as kindly mentioned Professor Fomin, that we have developed special vacuum technology to prepare very high quality nanolayers. It is important to make very, very mirror-like good quality interface, because ferromagnet layer serve like Fabry-Perot resonator, and it needs to be with good reflecting borders interfaces. And in such structure, we really observed all predicted by Tagirov behavior, from shallow minima up to deep oscillation of critical temperature depending on thickness of ferromagnet layer, up to reentrance superconductivity. And we prepared such switching element, but this element can serve like switching element, but it needs relatively strong magnetic field up to 1 kilorastet. It is a principle we demonstrated, but one shall use another physical quantum mechanical phenomena to reduce magnetic field. For this purpose, other well-known theoreticians Anatoly Fedorovich Volkan, Konstantin Borisovich Ifetov, Sebastian Bergeret, they and independent and simultaneously Mikhail Kupriyanov, Alexander Golubov, and Yakov Fominov. Yakov Fominov nowadays director of Landau Institute for Theoretical Physics. They investigated this contact between ferromagnet and superconductor, and they found that it can exist not only large enough full differential phenomena, but it can appear also triplet pairing, not usual BCS, Barton-Cooper-Schiffer singlet pairing, when two spins opposite, but collinear spins, but order parameter became very complex, like a helicoidal in space, and so-called triplet component, if you have two ferromagnetic layers and not opposite magnetization, but slight not non-collinear, by non-collinear magnetization can appear triplet component. For this purpose, it is necessary a very small magnetic field. Here is a theoretical prediction how can change critical temperature dependent on angle between mutual magnetization of two layers. And this is our experiment, this is our technology, this is our structure, and this is our experiment. This is theoretician, the theoretical prediction, and this is, one can see that by non-collinear monetization, really very strong change of critical temperature memory elements. It can be, and the next idea was to use the Johnson junction with such artificial magnetic metamaterial as the spin valve. Here it is his characteristics. This is so it looks like this tiny feature, and this linear is the artificial metamaterial layer structure from superlunar ferromagnet. And one can use this Johnson junction like element of Johnson, like base element for neuron. This is sigmoidal transfer function or sigma neuron, but our brain has spike neuron or Gauss neuron, and using two such junctions, one can have the transmission function like Gauss-like or spike-like. That's why spike neuron one can create from two junctions shown in the upper picture. One need to connect these neurons by artificial synapse. For this purpose, it can serve also layer structure from superlunar and ferromagnet, and very thin superlunar layers have so-called kinetic inductance due to motion of Cooper pairs comparable with geometrical. Geometrical inductance has each conductor. Normal conductor has, and it depends only on the size of conductor. But if we reduce the thickness of film, then the kinetic inductance can be comparable with geometrical. And this kinetic inductance can be tuned by very small magnetic field. You see that up to between 10 and 20 erstat, we can change the inductivity of such layer. Here is this characteristic by parallel, anti-parallel magnetization of layers in such structure, and here one can see change of kinetic inductance. That's why it can serve like linear element, changing connection between Gauss neurons in superdata artificial neural network. And here is the examples of realization. Oleg Mukhanov in Argonne National Laboratory, and group of Walter Pogosov in Moscow Physico-Technical Institute, MIFI. They simultaneously, in parallel, they create such artificial neural network based on Johnson junction like neuron and kinetic inductance like synapse. That's why I just demonstrate how fruitful can be ideas from theoreticians. Theoreticians just proposed in 1964, Larkin and Ovchinnikov proposed. At that time, it was not developed appropriate technology. That's why it was in journals. When technology developed, then good experimentalists tried to do it, and then can be done, can be prepared artificial neural network. And one of the important results that these ideas now we can translate to our students, master students. our rector, he is a mathematician also, very robust. He asked me to introduce the new quantum informatics in Technical University. That's why what I explained nowadays, I give lectures for students. That's why it was also one goal of the European project SpinTech. Thank you for your attention and patience.
Da, mulțumim. Mulțumim. Eu am o întrebare în legătură cu baza elementară care ar putea fi la baza construirii rețelelor neuronale și a inteligenței artificiale. Deoarece ceea ce ați demonstrat, ceea ce a fost demonstrat, neuronii și sinapsele, era oricum bazat pe tranzistori. Deci din nou este vorba de chipuri și ajungem la aceeași restricție, de fapt, legea Moore. Actualmente toată inteligența artificială este bazată pe chipurile de silic, bazate pe silic, care
care există.
Da, care sunt elaborate de Nvidia, Meta, Google și așa mai departe. Sunt produse la TSMC în Taiwan sau în Seul și la baza lor stă mașinile ASML care sunt elaborate în țările de jos.
Exact.
Acum s-au ajuns la limită. Am văzut că și graficele care le-ați arătat, legea Moore de acum e moartă, cu siguranță.
Da.
Deoarece s-au ajuns la...
Deja 1000
de atunci.
Energy consumption.
Da, energie, da, asta e clar. Eu am în vedere până acum, deci densitatea tranzistorilor este limitată, deoarece s-a ajuns la rezoluție de 2 nanometri.
Încă mai grav problema, răcire.
Păi ok,
mai
asta
grav.
oricum e legată de chipuri. Și deci s-a ajuns la 2 nanometri și două limitări esențiale. Lungimea de undă, care știm că rezoluția nu poate fi mai bună decât lungimea de undă. Lungimea de undă utilizată de ASML este 13 nanometri. Acum ei au amăgit fizica limitării cu lungimea de undă prin suprapunerea măștilor.
Propagarea signalului.
Da, suprapunerea măștilor, manipularea optică și așa mai departe și s-a ajuns la 2 nanometri. De fapt, de 10 ori de acum lungimea de undă a fost depășită limitarea asta. Dar oricum rămâne a doua limitare, deoarece când ajungem la sub 1 nanometru, este vorba de undeva 10 straturi atomare, oricum aici este limitarea tunelării cuantice, care nu poate fi nicicum, nu poate fi eliminată. Tunelarea mai jos de 1 nanometru, tunelarea cuantice nu poate fi realizată starea 0. Starea 1 funcționează, starea 0 nu funcționează, toată algebra Boole este distrusă. De asta, care ar fi următoarea etapă a bazei elementare? Poate acestea spinele de valve ca să iei locul tranzistorului, în primul rând, și într-al doilea rând, ar putea el funcționa ca o bază pentru calculatorul cuantic legat de qubits. Sunt două de trecut la rețele neuronale bazate pe alte baze elementare sau la calculatorul cuantic care funcționează în baza qubitsilor. Care este legătura? Unde ar fi implementate aceste spin valve-uri?
Trebuie să fie compromis. În limba engleză. It is necessary to mention that it should be reasonable compromise. No doubt that the notebooks or smartphone will use transistors many decades because this technology is good developed, and for majority of tasks it is enough. The problem is in the big data transmission for space investigation, for communication. For this purpose, we nowadays, you are absolutely correct, nowadays we came to natural limit of further development of technology. For that purpose, it should be, it's necessary, it is not possible to avoid to use another principle. Quantum computer is very special, quantum informatics, it is, nobody will use quantum computer like notebook. It has special tasks, but it can resolve problems which cannot be resolved many thousand years shall be working time of usual computer for resolve some problems which can be resolved within several milliseconds by quantum computers. That's why we shall think about the reasonable compromise for which purpose we for engineering, for communication, it will be enough existing SMOS. SMOS is a huge amount of money was invested, investments. That's why this technology for many, many years is profitable. But for data treatment, data archivation, it should be cooled down up to helium temperatures, artificial neural network based on superdata elements, because the energy consumption for big data transmission will be 7 orders of magnitude less than by SMOS. For that purpose, it is done. Thank you.
Mai sunt întrebări? Deci, în particular, vă rog, înainte, mai avem de lucru, înainte de a trece la următoare, acolo este suc rece care dorește, poftim, biscuiți, dacă dorește cineva ceai, poftim, nu stați pe loc, mișcați-vă, luați, turnați în pahare. Acum următoarea prezentare va fi a domnului Vladimir Țurcan. Din nou ne întoarcem la topologie, deci prima prezentare a fost legată de inele cuantice, deci topologie și acum topologia și magnetismul.
Thank you. I would like to express my gratitude to organizer of this symposium for possibility to present nice results which were obtained in laboratory of academician Sergei Ivanovich Radoutsan, who his 100 years from his birthday we recently celebrated. And if he would be here with us, he would be very surprised to what level is reached in this interesting field, which he actually initiated in field of material science of complex magnetic semiconductors. So I will tell about magnetism and topology, mainly under the aspects of geometrical considerations and quantum effects, which are also important, and we'll try to give the answer on the last question of academician Ursaki about what are the next generation for neuromorphic computing. Yeah, and let's start. This is outline of my talk. So I will present some historical excursus in the evolution of magnetic recording in conventional magnetic recording, magnetic hard disks. Then, as I mentioned, we will go to some results about topological effects in real space and non-trivial magnetic texture, which are now skyrmions. Then realization in laboratory practice of the skyrmions on the racetrack for data recording. And finally, briefly, about possible implementation of skyrmionics in quantum and neuromorphic computing. So you can look on the left right corner graph, which shows the evolution with time of areal density of data recording. So, and you can see that in 1956, when first hard drive was introduced in industry, until 2005 or 2004, the density of data storage increased by more than eight order of values. 8 order of values. This is huge. This in 70 years, this is incredible results. Yeah, but you can see that after 2004, there's some tendency to saturation. So first, hard drives were based on longitudinal magnetic recording. Then people recognize that to increase the density of data storage is better to use perpendicular magnetic recording. So, this is image of a opened hard drive of capacity of 1 terabyte, with in which the areal density of recording reach highest 650 gigabit per square inch. To increase the capacity, you can build several such disks which on the top of each other. And the biggest capacity reported in 2023 by Seagate company. This is drive XSM with capacity 36 terabyte. This is huge. And all this novel technique, which is still developing, use not only perpendicular magnetic recording, but combination with energy assisted perpendicular magnetic recording. When during the writing, you apply additional current sources to this writing head, and this suppresses the noise and allows to reach more higher density. Other technique or other technology which allows to increase the density is heat-assisted magnetic recording, and also other magnetic recording, this which allows to increase finally such a higher density of recording. So, however, first, the optimistic forecast for 2030 is 1 petabyte hard drive. However, if I already mentioned, so this tendency to saturation is limited by a so-called superparamagnetic limit, which is about 1 terabyte per square inch. And at such a higher density, this thermal fluctuation can flip the magnetization of domains, and then data are lost. And in order to overcome these limitations, different how to say approaches were elaborated, but this limitation can be successfully overcome by new topological Wirps or named magnetic skyrmions. They were first experimental evidence for such objects were realized in metallic manganese silicide. So close to the transition temperature of about 30 K, it was found one pocket where by different technique, Lorentz term, it was realized that appear assembly of self-organized magnetic whirlpools, which have nano-size dimensions. So soon this finding was in 2009 realized by a group of Professor Fleiderer from the Technical University of Munich. Yeah. Soon after this, a huge amount of work was done to find the other materials, and it was recognized that to find such an object necessary to have not only magnetic ordering, but also structural, break of the structural symmetry. This is a necessary condition to realize such objects. And this is this slide presents how evolution of the publication in starting from 2009 when the first experimental observation was done. So publication, which includes the name Skyrmion, in this 2 years grows up to 100 per year. Next 2 years, you see up to 800 publications. This is not Moore law. This is much faster. And in next 4 years, it reached 2,000 papers in research on skyrmions. And starting from 2021 till present, we have much more than 2,000 new publications concerning the topological material integration with artificial intelligence. And so this is huge activity. And we are happy that on some, so in 2050, we were also involved in this activity. So here I want to present our most important findings, which were done in collaboration from scientists from Institute of Applied Physics and the University of Augsburg. First, our milestone, I would say, paper which really signify very important milestone in skyrmionic activity. This is experimental discovery of Néel-type skyrmions. There are two types of skyrmions. Actually, there are a lot of more than 40 times of different types of skyrmions, but the main two are Bloch skyrmions, which were observed in first finding by Professor Fleiderer. And the second is our finding is Néel-type skyrmion, where magnetization of this assembly rotates in from periphery to the center in a plane perpendicular to the plane. So we elaborated technology which allowed to grow nice single crystal of this compound, which is Lacuna spinel. The spinel, this is activity of laboratory of Sergio Radovazan's more than 50 years, this group of materials. And this compound is polar narrow gap semiconductor. It orders magnetically at around 13 K, and growth of such nice and large samples allowed to establish the phase diagram and appearance of this squirmionic phase. Next important result is related to finding of fractional antiferromagnetic squirmion lattice, which was done in collaboration between our institute and the Power Sharing Institute from Switzerland. So again, in a very interesting spinel compound, which is manganese scandium sulfide, is a highly frustrated magnet, no Jahn-Teller effect, no breaking of lattice symmetry, but nonetheless, we found that this system, due to strong anisotropic coupling, it realizes anti-squirmion lattice. This is very important result for realization of racetrack based on squirmions for magnetic memory devices. Next important finding, here, sincerely, we were not the first, but we were not the last. We were among the first, not the first, but among the first, who demonstrated appearance of squirmionic bubbles in Kagome ferromagnet, in metallic Kagome ferromagnet iron 3 tin 2. Here comes not only in play topology in real space, where we observe these squirmions, but also topology in inverse state. This is quantum effects. So, and in this, due to Kagome arrangement of magnetic spins, you have flat bands, you have Dirac cones, and you have this material manifest giant anomalous Hall effect, giant topological Hall effect, so which are very important for manipulation of movement of squirmion in real devices. Again, our contribution is elaboration technology of the single crystals, which are really very impressive. And together with in collaboration with scientists from University of Augsburg, we investigated how we can control the formation, nucleation of squirmionic bubbles by size or time. Excuse me. Yeah, by size constrictions and by application of magnetic fields. So recently we extended the range of appearance of squirmionic bubbles till 80 K, which is important for low temperature applications. This result was recently submitted to Applied Physics Letters. So, and the very important results obtained now in collaboration with big number of scientists from two institutes from Jülich-Forschungszentrum, University of Augsburg, Institute of Applied Physics, University of Oldenburg, Germany, Regensburg University, University of Louisiana at Lafayette, and Chinese Southern University of Science and Technology from China. So it relates to all optical stochastic switching of magnetization texture in iron. So iron 3 tin 2 in this quantum material. This is actually is named the first quantum squirmionic compound. Yeah. So now I go to the second part of my talk, and immediately, not immediately, in I would say 4 years after discovery of skyrmionic object, Nobel Prize laureate Albert Fert and his collaborator propose how to use this skyrmions for magnetic recording. So they elaborated the so-called racetrack memory. When you put skyrmion on a recording media, and by low electric currents, you can move the skyrmions and manipulate and organize them in different assemblies. Yeah. And it was elaborated also a strategy for design of skyrmion of different types using racetrack memory by other groups. Yeah, and recent results from 2003. This is laboratory elaboration, not all electrical 9-bit skyrmion based racetrack memory, which is designed using laser irradiation. So you can see how you can combine different logical states using with erasing and by using laser radiation. And this slide shows a comparison of the data storage by conventional recording, by domains, which I mentioned, and skyrmions. So size of skyrmions can be several nanometers. So this may be 5 to 10 times smaller than conventional domains. Energy consumption is huge, reduction of the energy loss, 10 to the 5 times than for conventional hard drives. So then because skyrmions are topologically protected, they are stable against defects. And although conventional magnetic recording is non-volatile, but over some times you know that it degrades. And skyrmions are highly robust and stable for much longer period. And the most important is, one of the most important, that skyrmion devices need no mechanical moving part. So together with a much smaller energy loss, this is a huge advantage for skyrmionic technology. So, and now very briefly, skyrmionic quantum computing. So it was shown that when you reduce the skyrmion size till 1 or 2 nanometer, it starts to obey quantum mechanic law. It imposed to follow quantum mechanic law. And for example, size of skyrmion or helicity of skyrmions are quantized parameters, and using different, for example, here you have energy barrier between two skyrmions with different helicity. Yeah, and they because of low energy consumption, they can go to so they can compete effectively with other. Compared to transistors or SMOS technology, this is huge advantage. And finally, what I mentioned, it was proposed that skyrmions can be also very effective for neuromorphic computing. So if you put skyrmions on they mimic brain activity, and they can save as artificial synapses or artificial neurons. And if you look for activity, they really can simulate the brain activity. Okay, thank you for the attention.
Da, mulțumim domnului Țurcan pentru această prezentare formidabilă. Deci, de fapt, dumnealui mi-a răspuns și la întrebarea precedentă care eu am pus-o domnului Sidorin, dar acolo era, pe de altă parte, era legată de limitările care sunt pentru legea Moore, care provin de la lungime de undă și tunelarea cuantică în calculator. Aici, domnul Țurcan a arătat că și în memorizarea magnetică există un analog al legii Moore, care din nou ajunge la limită din cauza limitării superparamagnetice. Și acum și aici și acolo trebuia de găsit o soluție care ar fi soluție și anume de bază elementară. Acum domnul Țurcan ne-a arătat că această bază elementară din punct de vedere a magnetism și a topologie ar putea fi schirmionii. Vă rog întrebarea.
First of all, thank you very much for your not only well motivated but highly motivating work for the future. Second, I like to emphasize again here that the heritage left by academician Rădăuțanu is really flourishing, and this has been a tremendous development in your recent activities.
Yeah, thank you very much for this question. Because I remember when I was a student and came from the Technical University in laboratory of academician Rădăuțanu, he just proposed me the topic for my PhD related to magnetic semiconductors. He was very receptive to novel ideas, novel materials, and indeed, I want to say that due to this property, extremely, how to say, he was very receptive to new ideas.
Visionary.
Yes, and his vision of perspectives was really amazing.
Thank you.
Mai sunt întrebări în particular pe urmă. Deci acum trecem la următoarea prezentare. Domnul Ceban, ne întoarcem din nou la tematica, continuarea tematicii prezentate de domnul Macovei, sisteme optomecanice hibride, vă rog.
Dear organizers, thank you for inviting me today. So my today's talk would be about optomechanics with artificial atoms, which is one of the main topics we do at Institute of Applied Physics and Laboratory of Quantum Photonics. And it's inevitably you should investigate this if you want to take quantum systems with artificial atoms. And I'll see why. So I'll give you a general introduction to optomechanics, then we'll focus on more specific effects that we currently investigate, which is quantum cooling, and give you the results. So optomechanics have appeared shortly after cavity quantum electrodynamics, where one of the first problems trying to address was what happens with the dynamics of optical cavity where one of the mirrors is able to move freely under the radiation force. So it's still being investigated with very big mirrors, very small mirrors. Another family of large investigation was made on the dynamics of an object able to vibrate that was put inside the optical cavity. And the experiments have evolved since much to very complex devices where the main goal was to capture, to confine one mechanical mode and one optical mode with quite good quality factor. What matters for us here, that some of these devices, like the disks, differently shaped photonic crystals, you can put an artificial atom on them. And that's what matters for us, because when you take an artificial atom in such devices, this emitter couples to both to photons and phonons way stronger than a few orders of magnitude stronger than the radiation force. So for these kind of problems, you can neglect the radiation force that was investigated previously and do a new kind of research, which we called hybrid optomechanics, because you use emitters. So we come from quantum optics. We investigate through the prism of quantum optics, but this becomes more and more a multidisciplinary domain. Now, one important thing, yeah, you can choose different emitters depending on what you need. Most of them operate at Kelvin temperature, so we are cryostat temperature, which matters, of course, for the emitters, but as well for the mechanical resonator, because here, when I say single mode phonons, I mean it at the cryostat temperature, where only the fundamental mode is excited. So here's some examples. One of the first experiments with a quantum dot on a photonic crystal, or a superconducting circuit with a vibrating membrane. No doubt the physics of interaction of each kind of artificial atom with the phonons, with the mechanical vibration, is different. From the analytical point of view, you can express their quantum dynamics via interaction Hamiltonian with efficient coupling, which is similar for all this kind of atoms. So many models are interchangeable depending on conditions. And what is interesting for quantum dots that I'll focus today is that their coupling with the mechanical vibration appears due to the deformation of this quantum dot and the exciton inside it, which is important for photonic applications, because in this case of quantum dots, you cannot ignore, in many cases, you cannot ignore the phonons because of small sizes of photonic device, of modern photonic devices, and because this coupling is intrinsic. Now let's go to a more particular case, our investigation on quantum cooling with quantum dots, and particularly with double quantum dots. Now, the main result we achieved is that when you consider an optomechanical device made of a mechanical resonator with a double quantum dot on it, and you consider its interaction both with a phonon bath, which could be the substrate on which the resonator is deposed, and its interaction with the photon bath, which is a thermal light, incandescent light, you can achieve a cooling of the mechanical resonator when the bath, the temperature of the photon bath is lower, slightly lower than the thermal, than the temperature of the phonon bath. In experimental case, you have a cryostat, you have a substrate on which you depose the optomechanical device. If you somehow manage to lower the temperature of the surrounding vacuum, of the surrounding electromagnetic environment, you can achieve cooling of this resonator. And it's interesting because it happens passively. And as I will show further, it happens because the tunneling of the electron between the two sides of the double quantum dot. Now, what I said. And this is different than quantum cooling that you obtain from single quantum dots, because in single quantum dots, you need to apply some kind of driving, like a laser driving in this case. So some external coherent driving of the dot. Now let's look close at our analytic model. So we consider a double quantum dot where the left side, the right side, the electron is able to tunnel between the two sides. You apply a voltage here. So you have electrons entering only from the left, exiting through the right. It interacts with the mechanical resonator. And of course, you have the environment here. Specifically, this quantum dot is prepared in Coulomb blockade regime, which means when one electron enters inside the dot, it doesn't allow the second electron to enter. It's important because we have the only quantum states that this dot can be prepared is electron in the left state, in the right state, or no electron in the dot. And when you look at the Hamiltonian of our system, you see that it's of the double quantum dot is represented by a two-level a qubit Hamiltonian, but with an additional term which represents the tunneling of the electron from the left and the right sides. You have the phonons, the coupling with the phonons, the photons, and the coupling with the photons here. The quantum dynamics of this system is given by Masa equation, where you have the coherent part, but also some damping phenomena, which are incoherent phenomena, like the flux of electrons passing through the dot and the losses of the mechanical resonator due to interaction with the environment. Now, what I would like to highlight here is that this system as it is cannot be solved directly. And mainly because we have here a multi-mode electromagnetic field. So what we have done in order to solve, we have applied the reservoir theory in order to express the contribution of the surrounding electromagnetic field as damping terms. So as an incoherent process. So we've done this by using the reservoir theory, by considering the reservoir made of surrounding photons. And we used, in order to solve it, the known Born and Markov approximation, which appears due to weak interaction of the quantum system with the reservoir, and the reservoir that has no memory. So any quanta that exits our system is lost forever within this approximation. And we are able to solve it, but only after doing some additional transformation. And the main one, if you want to do it yourself, would be to apply the dress state, so to diagonalize this term of the qubit and the tunneling. And within the new system bases and within new atomic operators, you get to a James-Cummings Hamiltonian that we know how to solve. You use it and apply it within the reservoir theory. You find some damping terms. Let's look at them. Here's the general Masa equation. Here are the new terms that have appeared, which depends on the mean photon bath and spontaneous emission term. That depends on the tunneling, because this quantity depends on the tunneling amplitude. And when there's no tunneling within the dot, when the two sides are completely decoupled, this rate, spontaneous rate, is 0, and this term disappears. So all this is about only double quantum dots where you have the tunneling between the sides. We plot these quantities. So we plot the spontaneous emission and the ratio between the photon and phonon bath mean occupancy number. And we look at the phonon number within the resonator. So here's the plane. You see here is the temperature of the phonon reservoir of the substrate. And the surface you see here is the phonon number of our resonator. And the main idea and the main result is that when the temperature of the photons is slightly lower than those of the phonons, you get cooling. And the stronger this difference is, the more cooling you get. So this is the result in preparation. I think in the next weeks or few months, we will publish it. And in conclusion, that's it. You have cooling only for double quantum dots that where you have that tunneling inside. This is a passive effect. This is an intrinsic effect, so you have to apply no external driving. And this cooling effect is sensible to small temperature difference, which is also important. So thank you very much.
Mulțumim. Rugăm întrebări. Da, poftim, domnul Fomin.
Thank you very much, for your very clear, very interesting presentation. And if I may continue this line of connections to our predecessors, you are already a grandchild of academician Kowarski. It's very nice continuation of the legacy of our famous academicians in the past. My question is very short. How large should be your systems of double quantum dots in order to have your theory applicable?
Yes, so for sizes, you have the resonators from hundreds of nanometers to micrometers.
Okay, wonderful. Then I like to recall one of the slides in my own presentation, that if you make self-assembled quantum rings, then they lead you not to rings, but to quantum volcanoes. And quantum volcanoes consist of two bumps, you may call them quantum dots, with a small rim between them. It means that your double quantum dot systems already exist, and it's not so difficult to fabricate them because this is a self-assembly. It's not atom by atom positioning, but they are formed in this nice shape of quantum volcanoes. And maybe it would be interesting for you to look into this eventual realization of your nice system. Thank you.
Thank you as well.
Încă întrebări dacă sunt? Nu sunt, da? Mulțumim. Da, am ajuns la finalul simpozionului nostru de astăzi. În primul rând vreau să mulțumesc tuturor participanților și îndeosebi prezentatorilor care au venit cu rapoarte foarte interesante. Vedem că avem multe grupuri de cercetători în două universități din Republica Moldova care lucrează în domeniul fizicii cuantice. Astăzi noi ne-am limitat la prezentări din fizica cuantică. Există la noi în Moldova și multe elaborări în domeniul chimiei cuantice. Avem laboratorul chimiei cuantice la Institutul de Chimie și tot în sala asta au fost în legătură cu aniversarea 95 de ani a academiului Bersucher au fost prezentate multe rapoarte din domeniul chimiei cuantice. Recent am avut și la școala de vară din acest nou calea spre descoperiri științifice, raportul prezentat de domnul Bersucher. Așa că avem două dimensiuni, dimensiunea fizică și dimensiunea chimică legată de efectele cuantice. Și în fizica cuantică nu sunt doar aceste grupuri care au fost prezentate, care au prezentat rapoarte astea. În domeniul fizici cuantice lucrează și grupul doamnei Clotișner cu magneții moleculari, acolo tot sunt foarte interesante efecte cuantice. Grupul doamnei Nicolaev și Conopca lucrează tot în domeniu și alte grupuri care în Moldova care lucrează în domeniul fizicii cuantice. Acum, deci dacă ne întoarcem la începutul prezentării domnului Fomin, deci este vorba de obiectivele strategii ale acestei noi inițiative. Dacă să vorbim despre infrastructura, creării infrastructurii, domnul Fomin tot a menționat că este puțin probabil ca noi în Moldova să creăm o infrastructură care ar fi la nivel mondial și din punct de vedere a concurenței. Acum, sigur că ne putem axa pe colaborare internațională. De acum prezența domnului Fomin și aici și în Germania și în Italia și peste tot, deși este de acum un exemplu de colaborare. Am văzut din prezentarea domnului Țurcan, deci o colaborare extrem de largă și cu Germania, asta în primul rând, sigur, că toată Germania acolo, Statele Unite și acum mai recent și China, așa că pe domeniul ăsta tot avem o activitate destul de largă, deci ori public awareness, de evenimentul de astăzi, de acum, este un element a public awareness. Și cel mai important, iată, ne oprim la primul obiectiv de crearea capacităților umane. Aici suntem mai prost, mai ales din punct de vedere a fizicii cuantice. Mecanica cuantică, practic, nu se mai predă în universități. Și aici, deci, domnul Macovei vine cu o inițiativă, poate totuși să reinițiem acest domeniu și să organizăm un curs de mecanică cuantică. Trebuie de văzut, de discutat în ce format și unde, fiindcă avem două universități, Universitatea de Stat și Universitatea Tehnică. La Universitatea Tehnică am văzut că domnul Sidorenko de acum are ceva legat de rețelele neuronale, informatică, da. Deci e posibil că la Universitatea de Stat atunci de încercat de organizat acest curs pentru studenți. Așa că, iată, deschide. A doilea file. Pe flash. Letter files. Și acum, deci, e sigur că noi o să plătăm pe pagina Academiei un raport în legătură cu evenimentul de astăzi. Da. Și e important că în acest raport noi o să prezentăm și această informație, fiindcă la noi informația a venit de la Ministerul de Externe în legătură cu această inițiativă lansată de UNESCO. Și persoana de legătură de la minister este domnul Alexandru Fazli. Și dumnealui ne-a trimis aici un link care să fie plasat pe pagina Academiei, un link în care orice grup de cercetători sau chiar persoane fizice care are dorință să participe în această inițiativă mai activ și mai concret, trebuie să se înregistreze. Și atunci o să fie formate grupuri de lucru la nivel european și la nivel mondial, grupuri de lucru, și fiecare grup poate să-și găsească nișa lui de activitate dar pentru asta este nevoie ca sau persoană fizică sau persoană juridică să se înregistreze și atunci să spui capacitățile, care ar fi interesele și așa mai departe. Posibil că acolo să fie și niște fonduri pentru activități care... De asta o să plasăm informație tot pe pagina Academiei pentru viitor, dacă orice doritor poate să conecteze. Deci asta e tot ce am avut noi astăzi pe agenda. Dacă mai sunt alte întrebări, propuneri pentru discuție, poftim, este deschisă.
Încă mai strâns colaborări.
Da, mai multe colaborări. Vă mulțumim pentru prezență. Da.